Let us continue the concept what we have been doing for the last few lectures, and in lecture 12 we have come to the particular point that how to get equation for liquid solution as well as solid solution, and that equation contains delta G value in pure condition for both A and B, and also it contains the entropy of mixing term along with temperature term. So, that means which is nothing but delta G mix. So, we will have our lecture 13, and in this lecture we will try to see the equilibrium condition along the common tangent for solid line and liquid line. In order to do that, we will just go back to the picture what we have drawn in our last lecture, lecture 12. This is the picture what we have drawn, and then finally after doing lot of calculations, lot of equation development, we have reached to this particular situation. And also we have seen that in order to find mu A for a solution, I can make use of this equation. Of course, we can also develop equation how to find the chemical potential of B, and let us start that part. I know G2 solid is equal to minus XA solid plus now G2S GXAS is equal to minus delta G0A S plus RT ln XAS minus ln XBS, and then from this part it would come 1 and from this part it would come minus 1, both would get cancelled. So, if I multiply with XBS, then it would be minus so this is equation, let us say 5 and this is 6. If I continue from the equation number what we have done in the previous lecture, so there we ended equation number 4, but now we have to start with equation number 5 and 6. So, if we add equation 5 and 6, then we get G2S plus XBS G2S. You see that this is these two, if we add this one and this one, so it becomes 1. So, this is minus delta G A 0 S. Here also if we add this quantity and this quantity, they would cancel, and if we add this and this quantity, they will become 1. So, finally, we would get R T ln X A S. So, this is equation 7, and this is nothing but mu A S. Similarly, I would get mu B S, that means chemical potential of B in solid solution, on the similar line. So, I can try to get another equation for mu B, and just to follow up what we have done in lecture number 11, if G2 is equal to XA mu A plus XB mu B, then XB equal to minus mu A plus mu B, and then if I multiply with XA and then add, this is let us say 8 equation, this is 9, if we add them we would get mu B equal to G2 plus XA G2 dxB. Since this one and this one if we add, they will be 1. So, then dG2S XB S equal to delta G0 AS plus RT minus ln XA S plus ln XB S. This would be minus 1 and here it would be plus 1. So, it would get cancelled because derivative of ln XA solid would turn into minus 1 if we multiply this term again, because XA plus XB equal to 1. So, now dxB of XA solid ln XA solid would be equal to minus ln XA S minus 1. So, then if we multiply this one with XA solid, so this is XA solid, this equation is let us say 10. See, if we add equation, this is addition, equation 5 and 10 addition, we would get mu B S equal to G2 S plus XA S G2 S S is equal to RT ln XB S. So, this is equation number 11. for equilibrium for component A in solid and liquid is nothing but mu A solid equal to mu A liquid. So, what we have calculated is nothing but mu A in solid phase and mu B in solid phase. Now, you have to also calculate mu A in liquid phase. Now, for equilibrium same of component B in solid liquid, it will be mu B solid equal to mu B liquid. And we have calculated these two quantities, we have to calculate this as well as this. And for this we have to make use of G2 of liquid solution. Now, we can write the G2 of liquid solution is equal to XB liquid delta GB 0, I can simply write liquid, plus RT XA liquid ln XA liquid plus XB liquid ln XB liquid, and it would follow the same way of calculating mu A as well as mu B in the liquid phase. In case of mu A, which is nothing but G2L plus XB liquid dG2L dXA L, whereas for in case of mu B liquid it would be G2L plus XAL dG2L dXBL. Now, dG2L L equal to, since this is in terms of B, so it would be minus delta G0 BL plus RT ln XAL minus ln XBL plus 1 minus 1. This is coming because of derivative of logarithmic term, and as well as there is a multiplication factor which is x by L or XBL. So, if I multiply this one with XBL the way we have done it here, then this is XBL, 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 that means in the liquid phase. So, this equation, let us say I term it as 12 and this is 13. If I add equation 12 and 13, we would get mu A liquid equal to, so this would get cancelled this term and this term would get cancelled. So, we would get RT ln XAL. Similarly, if I try to find out mu BL, so this is G2L dGXBL equal to delta GB0L plus RT minus ln XAL plus ln xbl minus 1 plus 1, and then if I multiply with xal, this is xal, then this term, and then if we add, this is equation 14, add equation 12, should be 14, then we would get mu bl equal to delta GBL, so 0 L plus RT ln XB. Now I can use this equilibrium conditions. So now my equilibrium conditions are mu A solid equal to mu A liquid. I can get mu A liquid equation as this one. So mu A equation RT ln XAL is equal to, I have already calculated mu AS, which is this one. So I can put that equation as minus, which is minus delta GA plus RT ln XAS. This is equation which is, let us say, equation 15, and similarly for another equilibrium, mu Bs equal to mu Bl, that case it would be mu Bl we have calculated, which is nothing but mu Bs. If I consider mu Bs is this one, so this is RT ln XBS equal to, and mu B is L is basically this one, which is delta GBL plus RT ln XBL. Just cross checking. Mu Bs is this, mu As is this, and then mu Al is this, and mu Bl is this. So I am getting equation 16. So now these two equations, if we see carefully, we have two unknown, because if we know delta Gm for pure A and delta Gm or pure B, then we can easily calculate delta G0 of A solid and delta G0 B for liquid. Now here if we see this term XAS and XAL, if I try to plot that miniature plot, so this is mu As equal to mu A liquid, this is mu Bs equal to mu B liquid. Now I am pointing these two lines, these 2 points. At this point I can have mu A solid, mu B solid, this particular composition, and this particular, this is for This is for I think this equation, if I go back to that particular plot, this is for solid, this is for solid, this is for liquid. So, these two compositions I can term in the form of XA or XB, both the time they are liquid. This sometime it becomes a little confusing, and this is XA solid, XB solid. Now, I can term XA liquid, so these compositions and these compositions. I can term XA liquid equal to 1 minus XB liquid, and this one I can write XA solid equal to 1 minus XB solid. So, actually we are having two unknown, two equations. So, now we can solve this particular, and to solve this we have to just express either liquid or solid composition with reference to a particular component, either A or B. Let us do it from the point of liquid, pure A, okay, from the point of A. So, now if I try to do little bit of simplifications here, so ln XA liquid by XA solid, I can write it minus delta G0 AS, then I can write XAL equal to XAS exponential minus delta 0 AS divided by RT. This is equation 17. Similarly, from this equation I can write ln 1 minus XA liquid minus ln 1 minus XA solid equal to minus delta GB0 L. Then I can write 1 minus XAL equal to delta G0 BL by RT minus exponential by 1 minus XAS. Then it would become 1 minus XAL equal to 1 minus XAS exponential minus delta G0B L by RT. So, we have equation 18. Now, interestingly, you can see that equation 17 and 18 can be solved because we have two unknowns. This is one unknown and this is another unknown. So, we can solve this. Solve equation 17 and 18. And the solution, if we see, that solution becomes, I can solve this. So, now I can get XAS, I can get equal to 1 minus exponential minus delta 0 B L divided by RT exponential minus delta 0 A S minus Similarly, XA L equal to 1 minus XA S. So, we have both these compositions. We have found out what is my XA composition and XA composition for solid and liquid state. So, let us stop here. We will continue in our next lecture that why these two solution for compositions at two different points where the phases are in equilibrium leads to a phase diagram, and that to binary phase diagram. Thank you.